This is a video about how to use Kirchhoff's loop rule and Kirchhoff's junction rule to solve what are called complex circuits. And I would say that a complex circuit is one that might have more than one battery, or in other words, a complex circuit is one that you can't solve simply by calculating the equivalent resistance of what's hooked to the battery and proceeding from there. The previous lecture sort of talks about using equivalent resistance and solving circuits if it's just resistors connected to one battery. But this is more than we can solve using those techniques. I put it to you that we can't solve that without the content of this lecture. So let's take an easier example. Computer lag. All right, let's take this example. What current flows through this resistor? Well, you might have some intuition for the idea that this sort of right side up 12-volt battery fighting against that wrong side up 4-volt battery, they sort of have a battery battle, and the result is that the combination of the two are like 8 volts, like one 8-volt battery across a 1 kilo ohm resistor, which would result in an 8 milliamp current. And that is true, and what I'd like to do now is prove that it's true. Okay, so it's like there's a battle of these batteries and an 8-volt total battery that's driving current through this 1 kilo ohm resistor. I'm going to prove this using what's called Kirchhoff's loop rule, and it says that the sum of the differences in voltage across a circuit, if I go through a closed loop, is 0. So check it out. If I start at this point, and if I walk around the circuit and end up where I started, then I'll encounter several changes in voltage. I'll encounter a change in voltage when I walk through this 12-volt battery. I'll encounter a change in voltage when I walk across this resistor. And I'll encounter a change in voltage when I walk across the 4-volt battery. So here's what I'm going to do. I'm going to start by making two arbitrary choices. And I want to really draw attention to the fact that these are two separate, both arbitrary choices. I'm going to assume that the current flows in this clockwise direction. And maybe that makes sense because I can tell that the 12-volt battery is going to win. But it is actually an arbitrary choice. If I assumed that current flowed in the counterclockwise direction, I would end up arriving at the same solution. I'd end up getting a negative value for this unknown current. The goal is to find the current around the circuit. And if I assumed that it went counterclockwise, I would get the correct value. It would just be negative. So an assumption of the way current flows in this loop is one arbitrary assumption I made. Another arbitrary choice is what direction I would like to consider myself as walking in. I am going to choose clockwise for no particular good reason. Could have also chosen counterclockwise. But working now from those two arbitrary choices, a current that I've decided to call clockwise, and a loop that I've decided to go on clockwise, I can write down about the changes in voltage I encounter. Here's what I get. First, I cross this 12-volt battery, and I gain 12 volts, right? The battery's job is to make sure this location at its top is 12 volts higher than this location at its bottom. So I gain 12 volts, and then I cross this resistor. And do I gain voltage when I cross that resistor or lose voltage across the resistor? Here's the rule. If the direction you have arbitrarily chose to walk in is the same direction as you have chosen to call the current flowing, then you will lose voltage. If I'm going from the top to bottom of this resistor, and current is also flowing from the top to bottom, then you can see that I'm falling from, I guess, a higher voltage to a lower voltage. That's a negative change in voltage. Gain 12 volts, lose an amount of voltage equal to, let's see, by Ohm's law, the current through the resistor times the resistance of the resistor, minus 1 kilo ohm times the current. And then when I go through this battery, I lose voltage again, because this battery's job is to make sure that this positive terminal is 4 volts higher than the negative terminal. So when I pass from the high to the low, I lose voltage. So check this out. I've recorded the changes in voltage as I make a complete loop, and while the voltage where I ended is the same as the voltage where I start, so the change in voltage is 0 when I sum around the loop. That is Kirchoff's loop rule, that the sum of the delta V's around a closed loop is 0. Okay, so now I have an equation that I can solve for the unknown current. Boom, 8 milliamps. And that's what we guessed when we figured that, oh, this 12 plus that 4 is probably like an 8. But I'm going to do a more complicated example that involves Kirchhoff's loop rule, where we wouldn't have been able to generate a good guess. By the way, as I said, if you don't know which way current flows, make an assumption. Math will give you a negative value if the actual answer is opposite to what you assumed. So if I had assumed that current was flowing this way, but still arbitrarily chosen to walk clockwise, I would have gained voltage. Now, I guess an assumption that the current flows down on the left side, well, by the continuity of current would have to be flowing up there. So as I walk from this high to this, from this location across the resistor to that location, I'm walking against the current. I would gain voltage instead as I write my equation. Plus 12 plus I times 1 kilo ohm minus 4 is 0. That would give me an 8 milliamp solution. All right, so now that we have that skill, I would like to deploy it on the original problem that I asked. I've replaced the values in this complex circuit with variable expressions for the EMF of this battery, the EMF of this battery, and the resistances of these 3 resistors. All right, I would like to start by making some arbitrary choices. We don't know what direction the current flows. And actually, there are multiple currents that we don't know what direction they flow. Consider this branch. We don't know if the current flows downward or upward. But I'm going to arbitrarily say, oh, let's imagine that the current flows downward. Saying that the current flows downward here is the same statement as saying that it flows to the right there and flowing to the left there. See how that's true? So left here, down there, and right there is one arbitrary choice. A second arbitrary choice is in this middle branch, we don't know whether the current flows down or up. And in this right branch, we also don't know whether the current flows down or up, but well, I'll just decide, hey, down. And saying that this I2 flows down is the same as saying that that I2 is the amount of current flowing to the right through that battery and then to the left down here. So we don't know how much current is flowing in each of these 3 sections, and we don't know what direction it's flowing. So we're going to call it variables I1, I2, and I3, and we're going to say arbitrarily that they're all down. And you'll see why we need to make that arbitrary choice later. I'm also going to choose to walk around this loop in this direction. Could have walked around it in the other direction. And I'm going to end up writing down a Kirchhoff's loop rule for that path that goes clockwise. I'm also going to choose to walk around this loop in the counterclockwise direction. Could have chosen a clockwise direction. Now that I have made the choices about what direction I want to call the currents as going and what direction I want to walk around the loop, here's the blue loop. When I walk this way, I'm walking across the wrong way of the battery. I lose... Oh, wait, I'm sorry. You know what? I'm sorry, I made an error. I am not choosing to walk across through this left loop. This equation here indicates that I've chosen to start at this point and walk through the loop this way. When I do that, I'm walking in the same direction as the current is going. Note that both of my arbitrary choices came into play here. I am choosing to walk across this R1 resistor top to bottom, and I've also chosen to say that the current flows top to bottom. That means I lose voltage. When you walk the same way as the current you've chosen, you lose voltage. When students come to me and say, I don't understand this homework example because I don't understand when there's a minus sign and a plus sign in front of these changes in voltage across resistors, I say, here's the answer. When you walk in a loop across a resistor in the same direction as the current you've chosen, you lose voltage, minus I1 R1 for here. Now, when I'm walking through this resistor R3, I'm walking up opposite the current that I've chosen to call I3 in that direction. And so I'm gaining voltage. Current is really flowing downward, then walking upward through the resistor gives a gain in voltage. Okay, so that, and then plus epsilon 1, the EMF of the first battery, gives I'm back to where I started, and so that voltage change plus that voltage change plus that voltage change must be equal to 0, because there's no voltage difference when I walk a whole loop and arrive at the same place where I started. Okay, the right loop, in this one I'm wrong again. I'm actually choosing to walk in this direction. Okay. I walk with the current across R2, lose voltage of I2 R1 minus I2, minus I2 R2 is the voltage drop across there. Then I walk opposite the current when I go up R3. Then I gain voltage across that battery, plus epsilon 2 equals 0. Well, there are three unknowns here. I don't know how much current flows in this segment. I don't know how much current is flowing through the middle branch, and I don't know how much current is flowing through the right branch. So I need a third equation. Three unknowns need three equations. And you might think, well, maybe you get your third equation from taking the whole loop and walk like all the way around it. But it turns out that that is not true. This equation is the same as this first equation minus this second equation. You can verify that's true if you want. But this does not contain new information about the three unknown currents. We need another statement, and that other statement is Kirchoff's current law, Kirchoff's junction rule. It says that the sum of the currents entering a junction is equal to the sum of currents leaving a junction. That makes sense. That's the statement that current is conserved. The sum of the currents into a junction is the sum of currents out. So like if I had a branching like this and the current split up like that, I would say that this amount of current down is equal to that amount of current out plus that amount of current out at that junction there. That's the conservation of current. So let's consider this point here. The sum of the currents in is equal to the sum of the currents out. Well, the currents into that junction are all three currents, I1 plus I2 plus I3. This is non-physical. You can tell that something's not right here. And the thing that's not right is that we assumed the wrong direction for one of these currents. It is okay that we assumed the wrong direction. For now, our job is just to write down Kirchoff's junction law, that the sum of the currents in is equal to the sum of the currents out. There are no currents out of that red node, so 0. Math is going to give us a negative value for one of these currents, and that's going to be the resolution to this seeming paradox that it's impossible for all the currents to go in with none coming out. Now I'm going to plug in some values, and I'll just go through this quickly because this is just me writing down the equations that I had given before, but I left a little space here, and I left a little space here. And the reason that I left space there is that I'm about to use a matrix. I'm about to use a matrix operation. And I'll show you what that looks like. Oh, yep, there's the matrix. A matrix is a way to get your calculator to solve a system of equations quickly. And here is the way. Let me just do this right quick. I'm basically going to say to my calculator, hey, calculator, solve that system of equations. Here's how I'm going to do it. I'm going to say 1 of I1 plus 1 of I2 plus 1 of I3 is equal to 0. Minus 10 of I1 plus none of I2 plus 10 of I3 is equal to minus 12. and none of I1 minus 10 of I2 plus 10 of I3 is equal to minus 20. Here's the way that I enter this into my calculator as a matrix. I press the matrix button, then the edit, then I scroll down to option A, and the calculator is like, what shape do you want this matrix to be? How many rows and how many columns? I'm like, 3 by 4, 3 rows, 4 columns. Then I type in these values, hitting enter one by one until I've entered this matrix into the calculator. Note that here's like, it's kind of like there's an equal sign there in the matrix. This is just the way that you enter the system of equations into your calculator. Then what I'm going to do is I'm going to take what's called the RREF, the reduced row echelon form of the matrix. That is basically the command to solve this system of equations. I do that by going to matrix, then choosing math, and then choosing option B, which is RREF. And then it's going to be like, what would you like me, the calculator says, what would you like me to take the RREF of? And our answer is, take the RREF is of the matrix that we just called matrix A. And so this was matrix A, and so you, after you enter the RREF command, you go back to matrix and choose A. And then it gives you this as an answer. And what it's telling you is 1 of I1 is equal to 0.13 amps. I1 is equal to 0.3 amps. I2 is equal to 0.93 amps. And I3 is equal to minus 1.07 amps. So what does that negative sign mean? It means that I3 does actually not flow downwards. It flows upwards. That kind of makes sense now that I look at it, that this battery is driving current around there, and this battery is driving current around there. So they both tend to drive current up through this middle branch. The current is not downward as we assumed, it's up. So that's that. I will leave you to take a look at the worked out WebAssign questions about current density, and I would especially take a look at numbers 3 and 4 on the WebAssign. Number 3 is an exercise just like this. See if you understand the solution. And number 4 involves the choice of a very clever Kirchoff loop in order to solve a problem.